In the previous video, we talked about subgroups of a cyclic group, and in this video, we're going to talk about all the subgroups of a cyclic group, meaning that we're going to try to characterize all of the subgroups of a given cyclic group. So one thing that we talked about in the last video is that there's basically two different kinds of cyclic groups, two different kinds of cyclic groups. There's infinite, in which we have some G equal to the group generated by an element A, which ends up being basically this long infinite list of powers. And all of these powers are different from each other because we found out that if the order of A is infinite, then the only way for two powers to be the same is if the exponents are the same. So in the infinite case, that's the group. In the finite case, G is, again, the group generated by A, but this time A has finite order, which is n. And the group consists of just A to the 0, A to the 1, A to the 2, all the way up to A to the n minus 1. And then A to the n is equal to A to the 0 because that's the identity, and A has order n. So in this video, we're going to talk about what are all of the subgroups of a cyclic group in each of the cases. So let's start with the infinite case. Well, one thing that we know is that we can always construct a cyclic subgroup. And by the way, in the last video, the major result, and the one that we absolutely ought to mention here, is that every subgroup of a cyclic group is cyclic. In fact, let's put that in nice big text over here. Every subgroup, all caps, of a cyclic group is cyclic. So what this means is that if we want to find all of the subgroups, then all we have to do is investigate the subgroup generated by X for every group element X. So in the infinite case, we can always generate a subgroup by just picking one element, where K is some integer. And then what subgroup would that give us exactly? Well, that's going to give us the group consisting of all powers of A to the K, which means we have all powers A to the Kn, where n is an integer. And mostly these are different. The only time when these might be the same is if, for example, I take the subgroup generated by, say, A to the 5th, and I'm just picking the number 5 as an example. Well, that would be the subgroup consisting of all powers of A where the exponent's a multiple of 5. So I'd have like A to the minus 10, A to the minus 5, A to the 0, A to the 5, A to the 10, and so on. Now, can you think of any other element of G that I could take that would generate exactly the same subgroup? I mean, A to the 10th wouldn't work because that would only give me multiples of 10, not multiples of 5. But if I took A to the negative 5, well, that would give me exactly the same set because multiples of negative 5 are the same as multiples of 5. But aside from that little exception, the fact that we have to look out for opposites of the same exponent, other than that, all of these subgroups are going to be different. So an infinite cyclic group has infinitely many different subgroups. And there are infinitely many because we could take any positive exponent here and get a completely different subgroup. All right, so that's the infinite case. What about the finite case? That one's a little bit more interesting. Well, in the finite case, I could... Oh, wait a minute. Before going on, I want to make sure and mention, even though I never said that we couldn't do this, in the infinite case, we could always take the subgroup generated by A to the 0. That's the identity, so that's just the subgroup consisting of 1. You could also call it this, just the subgroup consisting of A to the 0. And that falls perfectly in line with our previous observations because, well, this is just the set of all powers of A where the exponent's a multiple of 0 because, well, how many multiples of 0 are there anyway? Just that one. So anyway, in the finite case, we have many different possible subgroups. We have the subgroup generated by that one, and the subgroup generated by that one, and the subgroup generated by that one. And of course, the subgroup generated by A to the 1 is just the subgroup generated by A, which is the entire group, because that's how we define G. But we still have all of these other ones. So we have as many as n possible different subgroups of G. But are these all different? And it looks like in most cases, the answer is probably going to be no. Because if, for example, my n was equal to 12, so A was an element of order 12, and G was a group of order 12, a cyclic group of order 12, then, for example, the subgroup generated by A to the first would be, well, it would be the entire group G. It would be the set of all powers of A from the 0th to the 11th. But then the subgroup generated by A to the 11th, well, what would that be? Let's just pull up here and find out. That subgroup would consist of, well, it'd have A to the 0 in it still, and A to the 11th, and A to the 22nd, and A to the 33rd. And on the surface, that looks quite different, but that's really A to the 0, A to the 11th, and then A to the 22nd, because 22 is congruent to 10 mod 12, and the order is 12, that's the same as A to the 10th. And then 33 is congruent to 9 mod 12, because those differ by 24. So really, you end up getting the same stuff, just in a different order. So that's really the same thing as the subgroup generated by just plain A, or A to the first. Okay, so I've listed n-1 things that look like subgroups, but they are probably not n-1 totally different subgroups. So which ones are actually different ones, and which ones are, interesting ones? So one thing I'm going to do to investigate this is I'm going to choose to look at, so this is an idea, look at the smallest power, smallest positive power of A in my subgroup H. Okay. Now, first of all, it's possible that there is no positive power in the subgroup H. It could be that H is just the subgroup consisting of A to the 0, in which case there is no positive power. So that's case 1 right there. But case 2 is that I actually do have a positive power, which means I will have, by well ordering, a smallest positive power. So suppose the smallest positive power is A to the K. All right. Now I claim that A to the K, or rather that K, has to divide in the order of my original group G. Now here's why that has to be the case. As usual, in order to prove that K is a divisor of n, I'm going to try and set up, not exactly a contradiction, but set up a remainder and show the remainder is 0 by using the division algorithm. So by the division algorithm, we know that n is equal to kq plus r for some integers, q and r, with 0 less than or equal to r less than k. All right, so in that case, one thing that I know is that A to the n is in H, because the order of A is n, that means A to the n is 1, and the identity has to belong to H. So that means that I know that A to the kq plus r also belongs to H, because that's exactly the same thing. N is kq plus r, which means I can say A to the k raised to the q times A to the r belongs to H, because I can just use properties of exponents to rewrite this expression here. So now moving up a little bit, I also know that A to the k belongs to H, because I declared k to be the smallest positive integer k, such that A to the k belongs to H. Sorry, when I wrote this earlier, I think I was a little bit unclear. So suppose the smallest positive power is A to the k. I mean the smallest positive power in H. Sorry about that. Okay, so I'm saying A to the k is in H. So I have this whole thing, because it's a power of an element of H. That whole thing is in H. And then the entire product is in H. So by the same kind of argument I used in the previous video, I can say that A to the r has to belong to H. And just to flesh that out a bit, I know that this element belongs to H, And I also know that the inverse of this element belongs to H. So I can multiply these two, and by closure, that product would have to be in H. So just elaborating that argument a bit. Sorry, and that's more than I wanted to write there. There we go. The inverse of that times a to the k to the q times a to the r. That all has to belong to H, which means that a to the r has to belong to H. And because r is less than k, and I said k was the smallest exponent that puts us in H, r has to be 0. This is by minimality of k. So r has to be 0, and that means that k is absolutely going to divide n. So since r equals 0, we have n equals kq, so k divides n, which is what we wanted to show. Okay, so what's the takeaway of all this? I mean, that argument's a little tricky to set up and follow. I would encourage taking a look at it again, just to make sure you understand the details. But for now, the main thing I want you to take away here is that all of this implies that unless I'm working with just the 0th power of a, which is case 1, in case 2, if I have any positive power at all, the smallest one has to divide the order of g. So if, for example, the order of g, or the order of a, is 12, then the smallest positive power in a subgroup must be one of the following. Must be either a to the first, in which case I'm just dealing with the whole group. So that's the one in which I get all of g. Or a squared, or a cubed, or a to the fourth, or a to the sixth. I guess I could also say a to the 12th. So I guess really that case I set up earlier where I said there is no positive power of a in the subgroup, that was kind of silly of me because there's always going to be a positive power. That would be a to the n. A to the n would always be in the subgroup. All right, so really this case doesn't actually exist because I can always find a positive power of a that lies in my subgroup. All right, so anyway, anytime I'm talking about a subgroup in the case of order 12, that subgroup has to have as its smallest positive power one of these 6 elements. And in each case, I can say exactly what the subgroup is going to be, because if my smallest positive power is a squared, then I know I'll have a to the 4th, a to the 6th, a to the 8th. I'll also have a to the negative 2. Well, that's just the subgroup generated by a squared. And if I have a to the 3rd as my smallest positive power, then I know I lack a to the 1 and a to the 2, but I have a to the 6th, a to the 9, and so on. So that's the subgroup generated by a cubed. And the same reasoning goes for all these other ones. So that one's equal to the subgroup generated by a to the 0, which is the trivial subgroup. So now I can say that if I have a cyclic group of order 12, that group has exactly 6 different subgroups. And each one is generated by a power of a whose exponent is a divisor of 12. So in general, and I'm not writing down a solid formal proof of this, I'm just going to let you fill in the details on this. If G is cyclic of order n, the subgroups of G are just the subgroups generated by a to the k, where k is a positive divisor of n. And we discovered that that even accounts for the case in which I have the trivial subgroup, because in that case the k is just equal to n. If my k is n, then I'm just generating the subgroup generated by the identity.